by a second glass pane. In this case, you don't need a framing. The framing is needed for a single glass pane because a single glass pane wouldn't be mechanically sufficiently stable. Okay, then the module goes to the final test, which again is a visual inspection, in some cases also a mechanical test, but always an electrical test, which measures the performance of the module and which also measures the insulation resistance. Usually these modules are specified for 1000 volts, and there are also more and more modules in the market which are specified for 1500 volts. Okay, then of course we need some documentation, and also the quality management, of course, is involved here, and then it goes to packing and stocking and final shipment to the customer. Okay, here I show variations in module design with the EVA, which I said is a dominating polymer sheet. EVA is ethylene vinyl acetate, which is a polymer basically made by the ethylene group and the vinyl group. Okay, these the first two, these are the standard module designs. You see the first one, we have here the solar glass. Solar means, as I said, highly transparent by low iron content. Then we have the cells, the crystalline cells embedded in EVA here. And then we have the backside foil, which is usually opaque, also a laminate by itself, typically a triple foil, a triple laminate. Okay, and the second possibility is that we have a glass-glass module. A glass-glass module can then be without a aluminum frame because the two glass panes are stable enough by themselves. And then, of course, we only need solar glass on the light incidence side. That means on the back side, it can be glass of any kind. Usually it's just ordinary window glass. Okay, then there are some variations for special purposes. These are non-standard designs, but for example, you see as a non-standard design, you also could have a polymer foil on the front side, and you could have, in principle, any carrier on the back side. In this case, it's a module. And of course, you could also have here a foil on the front side and on the back side, which in principle is also possible. But then, of course, you needed something for stabilizing because the crystalline silicon cells, they are very brittle. And of course, if you would bend such a module then too strongly, then of course they would break. In the case of thin film cells, of course, one could also make flexible modules. This is one of the advantages of thin film cells, but this is not possible for crystalline silicon cells. Okay, there are some further non-standard modules. You see there could be also other polymer materials. One widely used is polyvinyl butyral. This is the material which is usually used in laminated safety glass. For example, the windscreen of your car is also a double glass pane with this material in between. And it's very often used also in architecture, always where you need glass which does not break so easily and which has, even if it's broken, still some support ability. In this type of glasses, always this PVB is used, and therefore this is especially used in solar modules, where you use, for example, solar modules instead of a laminated safety glass, because then this usually has very similar properties to this laminated safety glass. In principle, you can also consider it being laminated safety glass. And in addition, just in the middle of the polymer, we have in addition these solar cells. So this is, of course, a very interesting application for architecture. Then another possibility would, for example, that you encapsulate it in Teflon. Teflon is polytetrafluorethene, and of course, it's one of the, how to say, best performing polymers, but it's also one of the most expensive polymers. And this could be an option, for example, for frameless special modules, for example, solar tiles. Then another alternative is to use, instead of the foils, use a cast resin. This is also an option for building because this is much better sound absorbing. Okay, sorry, I see here is an A missing here with a typo. Okay, and another one would be, for example, some thermoplastic polyurethane, which would have the advantage you could make the frame of this material, and you could also make the encapsulation polymer in this material. And of course, for the frame, you don't need a transparent form. And here, of course, you have to use a transparent form. That means this PUR or polyurethane is in principle a whole class of materials, which you get in various varieties. And this, in principle, there are many other examples thinkable how such a module could be made. Okay, here I show you just an example of a data sheet of such a module. In this case, it's from SolarWatt, which is one of the leading German manufacturers. That means it's one of the German manufacturers who has survived. And they, in principle, you see, they have occupied a niche market, which is the glass modules. But the glass modules market share is increasing because these glass modules, of course, they have a very high environmental protection. That means they are very stable. They have a slight disadvantage. They're a little bit heavier than a single glass pane module, but you see what they claim here, exceptional reliable yield rates, and also something which they call protection against PID, which is potentially induced degradation, which is a certain feature that some modules degrade under high potentials if there is a very high humidity around. Okay, fire protection. Okay, and usually this is for high power cells. Okay, this data sheet is now, I think, some years old. Okay, it's from 2017. At that time, this was quite a very good value. Meanwhile, of course, this value has even improved. Okay, here on the back side, you see, of course, there are a lot of mechanical data collected here. And what we see here, this is a glass laminate, and we saw also the solar glass is tempered. That means it's a thermally strengthened glass. That means this glass that does not break so easily, and this is in principle also standard. One of the glass panes in such a module is always thermally strengthened. Okay, you see this has 3 bypass diodes. Okay, I will talk about that bypass diodes a little bit later. The system voltage is 1000 volts, which is a standard still at the moment. And you see, if you look at the power, you see we have here 3 bin classes or 3 ratings of powers where the origin is this sorting of cell performance, and the main difference you see is the current. You see every of these sortings has a current of 100 milliamps difference. Okay, and you see there are also some thermal features. What we see here, there's a temperature coefficient defined for the power. There's a temperature coefficient defined for the voltage, for the open circuit voltage, and there's a temperature coefficient defined for the short circuit current. And what you can see, the coefficients for the power and the voltage are negative. That means with increasing temperature, these values become less, and we discussed it actually already in the unit physics of the solar cell, where the temperature coefficient for the short circuit current is 1 order of magnitude less, but it's positive. And this positive value here is due to the fact that the band gap of the semiconductor slightly depends on the temperature, and it becomes slightly less with increasing temperature, and therefore more photons can be converted to electron-hole pairs. Okay, this is about the module data and test conditions. There's basically the main test conditions is what is called STC, which is standard test conditions according to German, European, and international standards. And this means the solar irradiance or insolation is 1000 watts per square meter at perpendicular incidence. The spectral distribution is that of air mass 1.5. Okay, AM stands for air mass, and air mass 1.5 means that the light is incident by an angle such that the path length through the atmosphere is 1.5 times the thickness of the atmosphere. Because I guess you're aware of the fact, I mean, only between the tropics, the sun can be in the zenith, and outside the tropics, of course, the sun, even at noon, is under a certain angle. And so that this is somehow medium angle under which the altitude of the sun is usually observed. But of course, it's somehow arbitrary. But of course, one has to choose a certain angle, because the spectral distribution of the radiation, as we will see in next week's unit, depends on this air mass. That means the spectral distribution changes with the air mass, and therefore, of course, one has to choose one value of the air mass for which one specifies the spectral distribution. Okay, and the cell temperature is 25 degrees centigrade, okay, plus minus 2 of them. That means, and I underlined it here because you see here we have the cell temperature, whereas here for the NOCT conditions, the nominal operating cell temperature, we have the environmental temperature. And therefore, in these specifications, one always must take care. Does one talk about the cell temperature, or does one talk about the environmental temperature? Okay, let me explain what the nominal operating cell temperature is, which is also very important. Here we have a slightly lower irradiance, 800 watts per square meter instead of 1000. We have the same spectral distribution, again of AM 1.5. Now we have an environmental temperature of 20 degrees centigrade, with a wind speed of 1 meter per second parallel to the module, and we have open circuit conditions. And then the temperature which establishes for the for the cell and module temperature, precisely the cell temperature, but this is of course also the core of the module. This temperature is called the nominal operating cell temperature, and this temperature is typical 40 to 50 degrees centigrade for a module. But of course, it depends, of course, on the precise type of module. But this is the typical range here. And since the performance or the efficiency of a module becomes lower than the temperature, it's clear that at this temperature, the performance of the module is less than under standard test conditions. Okay, this is a selection of the module parameters as they should appear. No, these are not a selection, these are precisely the module parameters as they should appear in the specifications according to German or European standards for the rating of the module. You see, it's the behavior at standard test conditions, but it's also the behavior at the nominal operating cell temperature. And for all these, it's always the power has to be rated, the voltage, the current at the MPP, and then also the open circuit voltage, the short circuit current, and the efficiency. Okay, you see this example is obviously an older module because the efficiency here is, at least with respect to modern standards, it's moderate. Okay, then of course the maximum system voltage must be specified. I said already it's 1000 volts. There's a thing which is the reverse current capacity. Okay, here I have to, I will introduce this later. What this really means, it has nothing to do with the reverse bias regime of the diode. I will explain it in one of the later tuition units. Okay, then we have the temperature coefficients. Usually the current coefficient is called alpha, the voltage coefficient is usually called beta, and the power coefficient is called gamma. So these are quite typical values which are shown here for crystalline silicon. And I say it again, I mean the voltage and the power have a clear negative temperature coefficient. That means they decrease with increasing temperature, whereas the coefficient of the current is positive, but it's one order of magnitude less than this one of the voltage, and therefore also in the power, which is current times voltage, of course, the negative coefficient of the voltage is dominating. Okay, then of course the number of cells. I said already bypass diodes, I will explain. The ingress protection, of course, must be defined. Then some mechanical parameters, the weight, and there is also some warranty has to be defined. And yes, okay, these are the most important parameters, and you will usually find it in a data sheet of any module, and I wouldn't purchase a module where it's not specified. Okay, we know already here again with a sketch where the voltage and the current measurements are also indicated. You see if we have several cells in series, okay, it's only 3. The total voltage, what we get is the sum of the voltages, and the current is, of course, the current of the single cells. And if we have a parallel connection, the currents sum up, and the voltage is the same for all. And in this case, of course, if we would have one module with a lower voltage, then this lower voltage would determine the whole voltage of the modules. But I said again, I mean the standard connection within a module is series connections. There are just a few exemptions where we have, for example, 2 strings which are then connected to each other in parallel, but within each single string, again, all the cells are connected in series. Okay, this is basically repeating what I mentioned already in the physics of the solar cell unit, where we considered the irradiance dependence. You see here we have an irradiance which changes from 1000 watts per square meter to 200 watts per square meter. And the short circuit current in good approximation, or it's really precisely true, it's proportional to the irradiance, whereas the open circuit voltage is in good approximation proportional to the natural logarithm of the ratio of the irradiance and some reference value, which of course is needed to have the argument of the logarithm without dimension. And this is, you see, as the curves look like, and the dot here is always the MPP. That means you see with changing irradiance also the maximum power point changes, and especially the MPP voltage changes. It does not change very much, but it changes a little bit. And therefore, of course, the MPP tracker has to account for it. And this is, I should mention, because there was already a question in this respective tuition unit by one of you. This is at constant module temperature. And it's clear that in principle, of course, in reality, this is not true, because usually, of course, with the irradiance, also the module temperature will increase. But this is just to illustrate, if one just focuses on one single parameter, then we would have this behavior. These are the curves, how they depend on the temperature. And we see for the lowest temperature, we have by far the highest open circuit voltage. And the open circuit voltage really depends strongly on the temperature. You see the range here is from minus 25 degrees centigrade to 75 degrees centigrade. This is really a big change. Here we also see the slight change of the short circuit current, which goes in the opposite direction. But here in this picture, again, we see that the voltage dependence on the temperature is completely dominating over the opposite current dependence of the on the temperature. Okay, the lower curves are just the power curves. You see the power independence on the voltage. And here we see especially clear how the power really changes. You see at minus 25 degrees centigrade, the module has almost twice the power as at 75 degrees centigrade. This is really an efficient, a very, how to say, a very significant decrease. And now here's a promised picture, which I promised already in the second tuition unit, when there was this question that in reality, of course, the solar cell heats up. And here the two situations are compared. Here the hypothetical situation at constant cell temperature, but just to enlighten how it really changes when only the parameter of the irradiance is changed. And here you see here, we have this in the lower curve, we have the constant environmental temperature, again 25 degrees centigrade, how it changes then. And you see here, indeed, the open circuit voltage does not vary so much. You see the range of variation is less. And then, of course, you see it's also not such a clear dependence. Okay, it seems to even to increase slightly, because here this one, yes, this highest irradiance, yes, it seems even to increase slightly, because the cell cools down with decreasing radiation. And of course, this is only valid if one waits sufficiently long, such that the cell is again at the same temperature after an irradiance change. And of course, the precise behavior, of course, will also here depend very much on the module type. And you see in the upper case, the artificial case, you see the maximum power point voltage continuously decreases, whereas here typical, it first increases and then it decreases again. But you see the second one, of course, it's more complicated behavior. And this is the reason why usually, just to clarify what makes a simple single parameter, this is the reason why one usually looks at the hypothetical performance of the single parameter, because this is then helpful to understand this dependence. And then, of course, one can also construct or numerically calculate the dependence as it would be in the real case, where with varying irradiance, of course, the temperature of the cell would, or of the module, would change at a certain environmental temperature. Okay, I promised already that I will also explain a little bit about bypass diodes. There will be a dedicated session on this later, as you probably will know. But here's just a quick motivation. You see, if we have several cells in series, And then if one cell is fully or partially shaded, okay, in this case partially shaded, roughly 3/4 of the cell are shaded, 1/4 is unshaded, then we have a problem, because all these cells are in series, and I said already the weakest cell determines the current. And in this case, you see the current would be only roughly 1/4 of the current if all cells would be unshaded. And that means this one shaded cells makes all the not affected cells to reduce the efficiency. That means, you see, if this would be the situation, then we would lose 3/4 of the efficiency of the whole module. Now, if we have bypass diodes, which are bridging, in this case, half a module. And for small modules, it's standard that half a module is bridged. For bigger modules, it's typically 1/3 of the module. And for very expensive modules, for example, gallium arsenide-based modules, then of course, it could even be that every single cell is bridged by a bypass diode. And you see the bypass diode, if you look at the poling of the bypass diode, you see under normal operation, it's reverse biased. You see, this is the plus pole side, this is the minus pole side. That means under normal operations, these two bypass diodes are negatively biased. That means they are blocking. That means in principle, they don't affect the operation of the solar module. But if now you see in this half module, we have here this partial shading, then the current of the good half of the module can go over this, or at least partially. That means, you see, 3/4 can go over this bypass diode, and 1/4 can still go over this half module. And that means, at least for the half of the module which is not affected by shading, 100% of the performance is saved. That means, you see, here we would have still 100% performance of this half of the module which is not affected by shading, and we would have 1/4 of the performance here. And whereas in the first case, where we don't have bypass diodes, you see the whole module would deliver only 25% of the initial power, whereas here it's in principle it's 50% plus half of 25. Here it's still 62.5%. That means, you see, here we still have 62.5% of the full rated power, whereas here we have only 25% of the full rated power. And this is basically one of the purposes of this bypass diode, saving or rescuing a part of the power if we have full or partial shading. The second purpose is to protect the shaded cell, because the shaded cell can also be under danger. That means it could be operated under reverse bias, because it's clear, I mean, if this diode is to conduct the current, then of course we must have a forward bias across this diode, but a forward bias across this diode means a reverse bias across these solar cells. And this reverse bias especially will drop across this shaded cell. That means this shaded cell will be operated under reverse bias, and in worst case, without bypass diodes, it could be the reverse bias could be the sum of all the biases of the other cells, and that means the shaded cell is operated, or could be in the worst case, operated under a rather big reverse bias, and this might also destroy this cell. Therefore, the purpose of the bypass diodes is twofold. First, rescuing a higher power than without bypass diode, and secondly, to protect the shaded cells. But there will be a unit which is completely dedicated to this issue. The bypass diodes are usually in the junction box. You see this is a photograph of a junction box of a smaller module where we have only two bypass diodes, and the wiring is done in such a way that these two bypass diodes bridge half a module each. Okay, now what I presented now was all about crystalline silicon cells, but I said already that 5% of the market share is thin film modules, and therefore I will also show you in the remaining 10 minutes some facts about thin film modules. And in the thin film lesson, I indicated already that the thin film modules always have these stripes, and these stripes are series connected to each other. You see here, this dashed red line would be the current path, and as we can see here, it's series connected. Here we have the glass, then here we have the next one is a TCO front contact, then the blue one is the solar cell layer, and the gray one is the metal back contact. And in this case, where the light incident side is here the glass pane on which the materials were deposited, if this is the case, we call it the superstrate concept, because the glass pane forms the front side and is above, which means super in Greek, in ancient Greek. So super is from ancient Greek. But if we do it in the opposite way, you see when the light incident is the opposite side, then the deposition pane, then we call it the substrate concept. Sub means under, because in this case, the glass pane is really under the solar cells. But else is precisely the same. And in both cases, the module is completed by laminating this stack with a polymer and with a second glass substrate. Okay, this so-called monolithic interconnection is somehow simplified here. You see here from cell to cell, we have this precise series connection. If one looks more precisely to it, then it has this shape. Okay, in this case, it's just for the example for the copper indium gallium diselenide module, but it's the same for all the others. That means if one looks at it, one sees there's always a small part of the cell here, which is basically not used, because the current path goes from here to here, and this one again, but this is just due to the fact I said these are typical either laser cuts, this separation, or in case of copper indium gallium diselenide, the second and the third one are mechanical scribes, and the distance here is just a few 10 of micrometer, and this cannot be done so precisely such that one can really achieve precisely this form. I mean, the risk for shorts would be too big. Therefore, usually one accepts that there's a small part here, this middle part of such a very, very narrow, I mean, this is just a few 10 of micrometers here, that this is basically wasted active area, but this has to be accepted. Okay, here we see some encapsulation possibilities of these thin film cells. You see this would be, as it's a case for amorphous silicon and for cadmium telluride. Here we have the glass pane, and of course it's also solar glass on the light incidence side. And since this is usually heated in the deposition process, here we cannot use here strengthened glass. Here usually is non-strengthened glass used, but then the second pane is usually strengthened glass, because usually at least one of the two panes is thermally strengthened glass to make the module sufficiently stable. And in the other case, which would be the copper indium gallium diselenide, this would be the Okay, this one is the first one. This was the so-called superstrate case. This one is a substrate case, you see. And here, in both cases, we have then the EVA here also added as a second class pane. But the only difference is, you see, in the superstrate case, the glass pane on which the cell stack was deposited is then the light incident side, whereas in the substrate case, it's the non-light incident side. Okay, the first two, these are the standard cases, but of course one could, for example, also use a cast resin, for example, then one would get this case. But what one does see here is that in case of thin film modules, one always have double glass modules. This is necessary because the thin film modules have a bigger trend to degradation, and therefore they must be more protected against environmental impact, and there a second foil on the backside is not sufficient. One needs a second glass pane. The disadvantage of the thin film modules is that usually the fill factors are smaller. You see here on the right-hand side, that would be typical characteristics of amorphous silicon. Okay, in this case, depending on the cell size, because this is or on the module size, because this is one of the big advantages of the pros of such a thin film module, because you can make in principle any size you want. Whereas in crystalline silicon technology, it must be always multiples of these standard cell sizes. And you see, for comparison here, this is again a picture of the crystalline silicon cell. And what one sees, of course, I mean, you see the change of the current here, or the slope here is much steeper than in this cell. And also where we have here the maximum power point, here it's much smoother on the thin film side, which of course would mean that the fill factor is much lower, much lower, and therefore, of course, the efficiency of such a thin film module is lower than that of a crystalline silicon module. Here we see it for the copper indium gallium diselenide. You see the copper indium gallium diselenide looks better than the amorphous silicon, but also smoother than that of the crystalline silicon. Okay, these are just three curves for three different temperatures. Okay, and here an example of cadmium telluride, again at different temperatures. Okay, again we see here the big change with the voltage with temperature. Okay, it's a smaller change of the current with temperature, and we again see that the curves are much smoother than these of crystalline silicon, and therefore the fill factor is lower, and therefore the conversion efficiency is less. Okay, here is one thing compared. These are the temperature coefficients for Leerlaufspannung is open circuit voltage, Kurzschlussstrom is short circuit current, and then the fill factor, which is fill factor. And what we see, if we focus on the coefficients, we see that the first column is crystalline silicon, and all the others are thin film technologies. What we see that the thin film technologies usually have smaller temperature coefficients. That means this is one of the advantages of thin film technologies, that the temperature dependence is not as strong as for crystalline silicon, and sometimes by the thin film manufacturers this is highlighted as an advantage, but one must always keep in